Hello, I'm Ed Murphy with the Astronomy Department at the University of Virginia, and this is Astronomy 1210, Introduction to the Sky and Solar System. This is Lecture 18, The Copernican Revolution. So in the last lecture, we saw what the ancient Greek astronomers knew about the universe, and we saw that they not only knew that the Earth was spherical, but they had precisely measured the size of the Earth. They had measured precisely the distance to the moon. They knew that the Earth was bigger than the moon and that the sun was bigger than the Earth. And they had also developed a model for how it is that the planets, the sun, and the moon orbit around the Earth. Claudius Ptolemaeus, the astronomer Ptolemy, in 150 CE, had invented a model that was so accurate that, as we will see, it was in use for over 1,300 years. So the period of time that we're going to talk about is one of the most remarkable times in human history, and it comes in the height of the Renaissance. So we will, in the next few lectures, be talking about Copernicus and the great astronomer observer Tycho Brahe, and Galileo and Kepler and Isaac Newton. Now, at the same time that we're talking about these scientists, we won't be talking about what else was going on in the world. But of course, you can see some of the other historical events at the time. At the time we're talking about Copernicus, we're also talking about Martin Luther in 1517, nailing his theses to the Wittenberg Church. Michelangelo and Leonardo da Vinci and Christopher Columbus are all contemporaries with Copernicus. In the next generation, we have Galileo and Tycho Brahe and Kepler all working together at the same time that Shakespeare is writing. Elizabeth I was queen, Bacon and Rembrandt. And then in the next generation after that, we get Isaac Newton and William Penn and Edward Teach or Blackbeard. And then finally, over here in the later part of this little timeline, we have the American War of Independence, for example. So this is what's going on in the world at the time these discoveries are being made. And the first person that we're going to talk about is Nicholas Copernicus. So Nicholas Copernicus lived from 1473 to 1543. Don't worry about the exact dates. I'm not going to ask you the exact dates that he lived. Just know roughly when they were. He argued that the motion of the sun and the moon and the planets could be equally described by a system where the sun was at the center of the solar system and the Earth was orbiting around the sun. That's a heliocentric system as opposed to the traditional geocentric system with the Earth at the center. The problem with Ptolemy's system was he was unhappy with the need for the equant. You might remember that the Earth wasn't at the center of Ptolemy's circles. The Earth was a little bit off on one side. What Copernicus believed with that was a mistake. He believed that there was a much better model. He believed that all motion should be uniform. That is, it should be circular and it should be at a constant speed. And so he thought that by putting the sun at the center with the Earth orbiting the sun, that he could do a better job explaining the motions of the planets in the sky. Now, it's important to know that Copernicus was not the first person in history to propose a heliocentric solar system. A Greek philosopher had proposed a heliocentric solar system almost 2,000 years before Copernicus, but it was ridiculed and was not adopted at the time. In large part because of the observations of parallax. The fact that if the Earth was really going around the sun, then shouldn't we see the nearby stars moving back and forth? So Copernicus proposes his heliocentric theory, and he proposes it in a book called On the Revolutions of the Celestial Sphere, De Revolutionibus as it's sometimes called. And on the first page, he has a statement in Latin that says, "We therefore assert that the center of the Earth, carrying the moon's orbit, passes in a great orbit in an annual revolution around the sun, that near the sun is the center of the universe, and any apparent motion of the sun can better be explained by the motion of the Earth." That is, instead of the Earth sitting still at the middle with the sun going around it, the sun is at the center of the universe and the Earth is going around it. And in De Revolutionibus, in On the Revolutions, he publishes a diagram of the solar system, which is the first, I would argue, truly scientific model for the nature of our solar system, with the sun at the center, Mercury and Venus in orbit about the sun, the Earth with the moon carried in orbit around the Earth, orbiting around the sun, and then Mars and Jupiter and Saturn, and then the stellarium, the stars out here at the very edge. So that is Nicholas Copernicus's model of the universe, the heliocentric model. As an aside, I will very quickly mention for students that happen to be on grounds at the University of Virginia that we're actually very fortunate here at UVA to have a second edition copy of De Revolutionibus. It's not a first edition. It was the second printing of De Revolutionibus, but that was printed not long after the first edition. The first printing was done. And it's over in the Special Collections Library. And I think something that students often forget about the university is that universities are working places. When we have a collection, like special collections, where we store very valuable and very rare items, it's not like a museum where those items are sometimes preserved and on display but not to be used. Quite to the contrary, in an operating special collections library like that, those items are there for you and me to use in our scholarship. I think one of the greatest things about the Special Collections Library is you can go over there and you can ask to see Copernicus's De Revolutionibus. And they will sit you down in a room. You'll have to leave your backpack and everything out of the room. They will bring to you a pair of gloves, and they will bring you and put in front of you De Revolutionibus. And you can flip through one of the most influential and important books in all of the history of science, and you can flip into the book and you can find this very diagram in our copy of De Revolutionibus. And you can do that over in the Special Collections Library. It's really a very special thing to do. Even if you're not a scientist, regardless of what academic area you study, think of some of the greats in your academic area, and some of their first edition or early edition books will be found in special collections. Take an afternoon, go over, request one of them, sit down with it, and look at it, and appreciate the fact that we're very fortunate to have such an amazing collection of items here at UVA. All right. Enough about that. Let's go back to cosmology. So here is a little more modern diagram of Copernicus's solar system. So the sun is at the center. We've got Mercury and Venus orbiting the sun. We've got the moon going around the Earth orbiting the sun, and then, of course, Mars, Jupiter, and Saturn out there. So the question I have for you is this learning catalytics question. Copernicus's heliocentric system was not widely adopted at first. Why do you think that many people just did not like the idea that the Earth was just one of many planets and was not the center of the universe? So in learning catalytics, this is a word cloud. You don't have to write a complete sentence. You certainly don't have to write a paragraph. I just want you to type in a couple keywords that explain why people just did not like the idea that the Earth was just one of many planets. All right, I'll be interested to see what your response is as to why people didn't like the fact that the Earth was no longer the center of the universe. There was another problem with Copernicus's book, and I have this learning catalytics question for you. Was Copernicus's model of the solar system able to predict the positions of the planets better than Ptolemy's? Answer true if it was and false if it wasn't. So could Copernicus's model, which we know today, of course, is the correct model, was it more accurate and better at predicting the positions of the planets than Ptolemy's? So go ahead and go out to Learning Catalytics and answer true or false on this one. All right, let's see what the answer to this one is. It turns out that there were many advantages to Copernicus's model of the solar system with the heliocentric, sun-centered solar system. First of all, it was much simpler in concept to have the Earth moving, because many of the motions of the planets that we see in the sky are actually caused by the motion of the Earth. It was much, much simpler and easier to understand a heliocentric system. It also provided a natural explanation for the annual motion of the sun against the background stars. The sun was moving against the background stars not because the sun is moving, but because we're going around the sun. It provided a natural explanation for retrograde motion. Copernicus understood that as the Earth going faster passes a superior planet, a planet that is further from the sun than we are, it will look like it's going backwards simply because we're passing it and we're going faster than they are. Another thing that I haven't really described in any detail, but Copernicus was able to use the size of the retrograde motion, how long a planet spends in retrograde motion and how big that retrograde motion is. He was able to use that to determine the distances to the planets. And from the distances to the planets, he was able to get the relative spacing, the relative correct, I might point out, spacing of planetary orbits in our solar system. It also provided a natural explanation for why Venus and Mercury are always close to the sun. And Venus and Mercury are always closest to the sun because they're closer to the sun than we are. When you are on the Earth and you are here on the midnight side of the Earth, when you are at midnight, you are facing directly away from the sun and you are looking into the outer solar system. You will never see Mercury and Venus at midnight because at midnight you're looking away from the sun. In fact, the only time you'll ever see Mercury and Venus is when you're looking towards the sun because they are so much closer to the sun than we are. Now, typically you're not going to see them during the day, but what can happen is just after sunset or just before sunrise, you can see Venus or Mercury in the sky, but they are always close to the sun. But here's the thing. Copernicus's model was not more accurate than Ptolemy's model. Copernicus could not predict the positions of the planets better than Ptolemy could predict the positions of the planets. And the reason for this was a critical mistake that Copernicus made. He believed in the Aristotle's view of the universe. Aristotle believed that the circle was perfect and that all celestial motions must be perfectly circular. He also believed that they must be uniform and at a constant rate. And Copernicus so believed this that when he put his planets in his solar system, they had to move around the sun at a constant rate, and they had to do so in perfect circles. And that meant that his model was no more accurate than Ptolemy's model. And in fact, Copernicus even had to add little epicycles to his model in order to better predict the positions of the planets in the sky. When we talk about Johann Kepler, we'll see how this problem was fixed. Kepler realized that the motions of the planets are not on circles, but actually on ellipses, and that their speed as they go around the sun varies. But that's going to come about 60 years in the future. So let's hang on to that thought. Okay. So, and I've answered this question. Why was it not more accurate? Copernicus followed the philosophy of Aristotle and said that orbits had to be perfect circles, so he had to add little epicycles to make it work. I just want to quickly mention a little bit of nomenclature about when we talk about planets. So let's talk about the Earth going around the sun. As we talk about the Earth going around the sun in Copernicus's model, we divide the solar system into two kinds of planets. There are inferior planets. Inferior planets are planets that are closer to the sun than we are. And superior planets are planets that are farther from the sun than we are. So the only inferior planets are Mercury and Venus, and the superior planets were Mars, Jupiter, and Saturn. And of course, Uranus, Neptune, and Pluto, but Copernicus didn't know about them. For a superior planet, there are two major events every year. One is conjunction, when the superior planet is on the opposite side of the sun from us. And the more important one, the far more important one, is opposition, when it is opposite the sun in the sky. That's where opposition comes from. And opposition is when the Earth and the superior planet are closest together. That means a couple things. First of all, if the Earth is closest to this planet, it means that the planet is brightest in the sky, and the best time of the year to observe planets are when they are at opposition. And because the Earth goes around the sun once a year, typically the outer planets come to opposition about once every time period that's a little bit longer than a year. The reason it's a little bit longer than a year is that the Earth goes around the sun in a year. When the Earth returns to here, that planet has moved on, so the Earth has to go a bit more to get the planet to come back to opposition. In most places, in most planets like Jupiter, Saturn, Uranus, Neptune, Pluto, it happens a little bit after a year. In the case of Mars, actually, it happens once every 26 months. And that's because once the Earth goes around and comes back to here 1 year later, Mars is actually on the opposite side of the sun. And so the Earth has to go a whole nother year and a couple months around before it catches up to Mars and gets to another opposition. But anyhow, a couple of things important about opposition. The planet is closest to the Earth. It is brightest, and because it is closest to the Earth, it appears biggest in a telescope. So opposition is when you want to observe planets with your telescope. The thing is, although opposition technically happens at one moment in time, there is one moment in time when the planet is closest to the Earth, really for a period of a couple months here, a month or two before opposition and a month or two after opposition, the planet looks really good in the sky. So you don't have to observe it exactly on the night of opposition. A few months before and a few months after are really good. And the planet will be highest in the sky at exactly midnight, because here's the sun. Exactly opposite the sun, this is the midnight line right here. So superior planets, when they are at opposition, they are best visible at midnight. For an inferior planet, there are two conjunctions. There's superior conjunction, where it's on the far side of the sun, and inferior conjunction, when it's between the Earth and the sun. Inferior conjunction is when the planet is closest to us. The problem with it is it's in the same direction as the sun, and typically we can't see it. So although the planet is closest here, and you might think would be best for observing, it's actually not a good time to observe the planet at all, because the planet is very close to the sun in the sky. The best time to see the planet is at two times called maximum elongations. Maximum elongation is when the planet appears farthest from the sun in the sky. Now, what we mean by this is there's one in the eastern sky and one in the western sky, one in the evening sky, one in the morning sky. And what happens here is, as you're carried along the Earth just after sunset, just as it's getting dark here, you can look up, and in the evening sky, you can see the planet at its greatest eastern elongation. It appears farthest from the sun in the sky, and it makes the planet easiest to see. Most of the other times, the planet is so close to the sun that in terms of how it appears to us, that it's hard to see, but at the greatest elongations, it looks like it is at its farthest from the sun. Okay, so I've sort of answered this question for you. Sorry, I got ahead of myself, but let me go ahead and have you answer it in Learning Catalytics. When a superior planet is at its closest and brightest, what time of night is it highest in the sky? So there you go. For a superior planet, when it is at its closest and its brightest, what time of night is it highest in the sky? Go answer that in Learning Catalytics. Okay, so you might remember I gave the answer to this one away. Like I said, I got ahead of myself. I was so excited about talking about this, but the answer to this one is it's midnight, right? If this is the Earth turning around right here, this is noon, sunset, midnight, sunrise. When a planet is opposition, it is highest in the sky at midnight. All right. That's all I'm going to say about Copernicus, so let's go on. Actually, that's not all I'm going to say about Copernicus. Let me say one more thing about Copernicus. A couple more things, actually. So interestingly, during his life, Copernicus had come up with this heliocentric model. He worked with a friend of his by the name of Rheticus to publish a small summary of his ideas. And that summary was not well received. As we pointed out in this Learning Catalytics question a minute ago, many people did not like the fact that the Earth was just one of many planets. People believed that the Earth was special, that it was God's special creation. And if the Earth was just one of many planets going around the sun, then it wasn't special anymore. So Copernicus's summary of his idea received a lot of opposition. And Copernicus was hesitant to publish his whole book, his whole treatise, laying out his heliocentric model of the universe. But finally, late in his life, Rheticus convinced him to do it. Rheticus moved on to another job elsewhere and had to leave his friend behind. And as Copernicus lay dying, he was working on this great manuscript on the revolutions of the celestial sphere. And someone else was helping him out, a man by the name of Osiander. But interestingly, Osiander did not believe the heliocentric model, or did not want Copernicus and himself to get in trouble for publishing the heliocentric model. So interestingly, Osiander publishes a letter that gets inserted at the front of De Revolutionibus. And this letter says that everything you're going to read in this book is a mathematical description of the planets, but don't take it to be true. Don't believe that the sun is really the center of the solar system. The Earth is really the center, but this makes a nice mathematical model. And I think it's really interesting that Copernicus suffered this fate at the end of his life, that the preface that was attached inside his book actually claims that everything inside the book was not true. It is believed that on his deathbed, as he lay dying, Copernicus was handed a copy of his book. But possibly fortunately for Copernicus, he died just as his book was published, and so he missed all of the controversy that his book created. And also, possibly fortunately for Copernicus, he missed the repercussions of that. And we will see those repercussions fell squarely on Galileo Galilei, who we're going to see in our next lecture. But before we go on to Galileo, there's one more astronomer I need to talk about, and that is Tycho Brahe. Lived from 1545 to 1601. He is the last and the greatest of the pre-telescopic observers. Remember, we're still talking about a time here where the telescope had not yet been invented. All right. So Tycho Brahe was the greatest of the pre-telescopic observers in Europe. He noticed that tables based on both Ptolemy's mathematics and tables based on Copernicus's mathematics could not accurately reproduce the motions of the planets. When he was a young man, he had seen in the tables of the planets that there should be a close conjunction of two planets in the sky. The two planets should be close together on a certain day. And in fact, it was many weeks off. And he realized that we must be able to do better than this. We must be able to come up with a more accurate model to predict the motions of the planets in the sky so that we could predict better when they would appear close together. But he realized in order to come up with that model, he needed accurate measurements of the positions of the planets in the sky, and those did not exist in his day. So he spent more than 20 years measuring precisely the positions of the sun, the moon, and the planets with respect to the background stars to unprecedented accuracy. Now, Brahe was famous for a number of other things. In 1572, Tycho sees a new star appear in the constellation of Cassiopeia. Cassiopeia is the queen of the mythical kingdom of Ethiopia, looks like a giant W in the sky, and in 1572, Tycho sees a new star appear in that part of the sky. Today, by the way, we know that this was a supernova explosion. This was the death of a massive star. It detonated itself at the end of its life, so it was a supernova explosion. Now, here's the thing. Aristotle taught that the heavens were perfect and unchanging. In fact, the heavens were made of an element not found on Earth called ether. Well, if this new star caused the heavens to change, well, let me phrase that differently. If there was a new star, it could not be a part of the heavens. It had to be a part of the earth. Things on the earth were constantly changing, and that's because things on the earth were made of the four base elements of earth, water, air, and fire. And so things on the earth could always change. And if a new star appeared in the sky, it must be a part of the earth and not a part of the sky. But Tycho Brahe came up with a clever way of measuring the parallax of the star. If the star was really in the Earth's atmosphere and not a part of the distant celestial stars, well then as it rotated around the Earth, because remember, Brahe believed that we were on a geocentric system, an Earth-centered system, so he and the Earth are sitting still. As it orbited the Earth, as the whole celestial sphere turned, when the star was just rising up, we should see it against this background. And then as the star moves across the sky, when it's setting, we should see it against that background. That is, if the star is really in the Earth's atmosphere, it should be shifting back and forth during the course of the day. And Tycho tries to measure this, and he can find no parallax at all. And he knew then that this new star had to be further away than the moon, because even Ptolemy could measure the parallax of the moon. Tycho Brahe could measure the parallax of the moon. But this thing had to be so far away, because he couldn't measure its parallax, it had to be further away than the moon. Well, the moon was already up there amongst the stars, so this thing had to be up there amongst the stars. And that meant Aristotle was wrong. The heavens are not perfect and unchanging. And based on this observation, the Danish King Frederick II offers Tycho the island of Hven, where he constructs a famous observatory called Uraniborg. So this is his observatory at Hven. You'll notice that there are no telescopes at this observatory. This is still before the invention of the telescope, but he creates these giant mural quadrants, as they were called, these giant, essentially, protractors for measuring angles in the sky so that he can precisely measure the positions of the planets in the sky. During his lifetime, there were a number of comets in the sky. And because comets move through the sky, and because comets change in appearance, the ancients believed that they could not be part of the stars. They could not be part of the heavens. They must be in the Earth's atmosphere. They must be a part of the Earth. But Tycho Brahe tried measuring their parallax, and again, he could measure no parallax. They had to be further away than the moon, which meant they were part of the heavens, and the heavens were not perfect and they were not unchanging. For more than 20 years, Tycho measures the positions of the sun, the moon, the planets in the sky. He actually rejected Copernicus's model of the solar system, the idea with the sun at the center, because Tycho was so good now at measuring parallaxes of things that he tried to measure the parallax of Mars. If the Earth was really going around the sun, we should see Mars shifting back and forth in the sky as well. And he thought he could measure the parallax of Mars, and he went out and tried it, and he could not. Today we know, again, it's because Mars is far enough away that he couldn't measure the parallax of Mars, but that's why he rejected Copernicus's model. He actually came up with his own model for the solar system, and his model, I think, is really quite clever, if kind of crazy. So the Earth is the center of everything, and the Earth is unmoving, and the moon is going around the Earth, and then there's the sun, and it orbits around the Earth, but everything else, Mercury, Venus, Mars, Jupiter, and Saturn, all the planets are orbiting the sun. But the sun is orbiting the Earth and the moon are orbiting the Earth. So it's kind of clever in that you get a system where all the planets are going around the sun, but the sun and the moon are going around the Earth, and the Earth is the one at the center of the universe sitting still. So Tycho Brahe wanted to revise tables of planetary positions, the tables that Ptolemy and the tables that Copernicus had come up with. But the mathematics was beyond him. He was not a good mathematician. So he hired a young mathematician by the name of Johann Kepler to help him out. And we'll see about that later on. So those are the early Renaissance astronomers. In our next lecture, we will talk about Galileo Galilei. And we'll talk about Galileo and Kepler, who were contemporaries. They came just after Copernicus and around the same time that Tycho Brahe was wrapping up his observations. So in the next lecture, we will talk about Galileo and Kepler, and I will see you then.